In this last video for section 1.2, we're going to go through the proof of the triangle inequality, which is problems number 46 and 50 combined in your book. And we're going to start with 46. So in problem 46, it says that the size of the real part of z should be less than or equal to the size of z, and the size of the imaginary part of z should be less than or equal to the size of z. Now, by size here, of course, I mean modulus, and modulus is a distance thing. So I'm not going to prove this algebraically. I'm just going to draw you a picture. So if we have a random z in the complex plane, there's some x plus iy, then the real part is here. So if this is our z, and the real part is the projection down onto the real axis. So that's our real part. Oops. Now, of these 2 points, of course, which is further away from the origin? Well, this upper point is further away. So let's just notice here, maybe on the side, z is further from the origin than x. And since it's further from the origin, the modulus represents the distance from the origin. So this is the same thing as saying the real part of z is less than the absolute value of that. That's the distance. We're comparing distance. Is less than or equal to the modulus of z. Now you could go in and you can play with the actual modulus to see that this happens. But I don't want to spoil 46 in that way, so we're just going to do a geometric argument. Similarly, the imaginary part is up here. Well, it's the length, it's the distance from iy to the origin, and that's also closer to the origin than z, so a similar argument applies. So that's 46. For the next step, in 50, we're going to prove both of these statements, and then we're going to see how they can combine to give us the triangle inequality. Should be an equals there. So, question is, well, why are these true? So let's not take, these are things we have to show, so let's put a question mark through them. I'm not sure if they're true just yet. So we want to show that the modulus of z1 plus z2 squared is the right-hand side. So let's start by computing the modulus of z1 plus z2 squared. So let's keep the right-hand side as our target expression. So the modulus of z1 plus z2 squared is the modulus of, well, z1 plus z2 times the conjugate of z1 plus z2. But conjugate breaks up under addition. So it's z1 plus z2 times z1 bar plus z2 bar. Now we're just going to FOIL everything out. So we're going to get z1 bar plus z1 z2 bar for our outside terms plus z1 bar z2 for our inside terms plus z2 z2 bar. And let me also notice that whenever you multiply a number by its conjugate, you get the modulus squared. This first and last guys will be the modulus of z1 squared and z2 squared. And then this middle guy is really z1 z2 bar plus z1 bar z2. Well, that's the same thing, but I can do z1 z2 bar and then put a bar over everything. Whenever you have a double bar, it cancels, so it's the same expression as before. But the point is now this is a complex number plus its conjugate. And by what we did earlier, we know that whenever we take a complex number and its conjugate and we divide it by 2, and we add them together and divide it by 2, we get the real part. So what we're going to get here, instead of, we don't have a division by 2, so we're going to get double the real part. As desired. All right, great. Now, for this next guy, we're going to compute here. Again, we're going to pocket, just like up here, we pocketed the underlined blue expression, and we found that we got that. We're going to pocket the underlined blue expression again, and we're now just going to play with the left-hand side. So when we square an expression, we always are going to get the first term squared plus twice the product of the first and the second plus the second term squared. But the modulus of a complex number plays nicely with multiplication. So this is just twice modulus z1, z2 plus z2 squared. Now we're going to combine these, and this is step, so we've achieved it. So that's step, this is C here. So z1 plus the modulus of z1 plus the modulus of z2 squared is equal to this number, or this right-hand side that we just computed. But we know by problem 46, let's even just scroll up and look at that real quick, that the modulus of a complex number is always bigger than or equal to the absolute value of the real part, which in turn is bigger than or equal to just the real part, right? Because if the real part is negative, the absolute value is bigger than it, and if it's positive, they're just equal. So we're going to use that right now. So this is bigger than or equal to z1 squared plus twice real part of, there's one intermediate step we have to do. Let's go back for a second. Yeah, we're going to go back for just 1 second. I realize I've written down B. What the problem says B is incorrectly, but that's okay. The modulus of a complex number is the same as its conjugate. We can just conjugate that guy. The reason why we want to conjugate one of them is to use part A. So now we can say bigger than or equal to modulus z1 squared plus twice the real part of this middle term plus z2 squared. And what was this? This was exactly the modulus of z1 plus z2 squared. So if we read left to right, we get the modulus of z1 plus the modulus of z2 quantity squared is bigger than or equal to the modulus of z1 plus z2 squared. And the finishing touch is we're going to square root both sides. And since the term that's being squared is positive on both sides, the inequality is going to stay. So when we square root the left-hand side, the squaring is going to go away. When we square root the right-hand side, well, the inequality stays, but then the squaring goes away as well. And there we have our triangle inequality.